All right, so in this video, I'm continuing on with page 4, and we're just looking at these standalone problems that, the directions are pretty straightforward, right? An integral or sum of integrals that could be used to find the total area. So we're only interested in total area. But you could see in a couple of examples, specifically numbers 3 and 4, that you're dealing with multiple functions, right? So if I want to find the area of the shaded region, and the region is already above the x-axis, that's actually the easiest possible scenario. What I can do is just kind of partition it into two separate areas, with one function being the dominant function over the first interval, and the second function being the dominant function over the second interval. Okay, so I'm looking for area between the function and the relevant axis. All right, so I'd be looking for the integral over the interval of 0 to 1 of x squared dx. All right, the second piece is it's a different function, and now we're going the rest of the way. So we're going from 1 to 2. Now we have the function 2 minus x dx. If we add those two integrals together, because both parts are above the x-axis, we don't have to worry about absolute values or anything like that. We'll have what we need. All right. So that's our that would be our total area. And again, we just need the integrals. We don't need the final areas. All right. So the next one, number 4, is essentially the same thing, right? Because we have two functions, and there's a change. There's a change in dominance. The dominant function is y equals the square root of x over the interval of 0 to 1. That's here. And then for the next piece, going from 1 to 2, we're now looking at just the x squared function. I'll talk a little bit more about the theory associated with this in a couple of minutes. But for now, it's just, let's get some answers. Get some answers down on paper. Yeah, so numbers 5 and 6. So number 5 it's a single function over an interval. And what we learned is, in numbers 1 and 2, is that if we want to find the total area, all we have to do is make the negative area into a positive area. And we can do that numerically by finding its area and negating it. We can, if we have some symmetry, we can make use of that. But what we could also do is a reflection of the negative areas. All right, so I'm just taking my negative area, making it positive, and I'm essentially making a new function to find the area between that function and the x-axis. All right, so this new function, this black function here, and you could verify this in your calculator. It's actually kind of a cool experience where you're like, well, how could that possibly work? And really, when you think about it, what does an absolute value do? It takes negative things and makes them positive. It keeps positive things positive. So why would it do anything different to a graph, So I think that's something that we very easily lose sight of when we're learning all of these different skills over the years. All right. Now, something else that's very easy to lose sight of is that when you're finding the area over an interval, what you're looking for is the area of a two-dimensional figure. So let me just do that real quick. I'm going to draw, this is the classic approach to this, but it's an oldie but goodie. It gets the job done. I'm going to draw an arbitrary rectangle, and that arbitrary rectangle is going to have a height of y. Let me thin that out. And some infinitesimal thickness or width that we call dx. All right. So a height of y multiplied by some infinitesimal thickness dx. That's an area, right? All right, so that's the area of that one arbitrary rectangle. What an integral does is it integrates all possible rectangles, arbitrary rectangles, from the beginning of your interval, to the end of it, puts it all together, and then gives you that sum total area. All right, so you're looking at, we have a disagreement. We have a y and we have a dx. But we know what y is equal to. Y is equal to x squared minus 2x as an absolute. So one way of correctly identifying the integral that would give us the total area here would be the integral on the interval of 0 to 3 of the y, that height y, which is now known as x squared minus 2x as an absolute value, times its infinitesimal width, dx. All right. Another way to handle it, so I'll write a little or down here, or we could have taken that negative area here, this negative area, same function, just go from 0 to 2. We'll have that function still x squared minus 2x, so the original one, dx. That would give us a negative area. If I want it to be positive, I could just slap a negative in front of it. And then add to that separately the area going from 2 to 3, same function, but this part of the function would give a positive area. When you put the two together, you would get the same answer that you would get for this. All right, so it ends up being the same thing, but I just look at it like, well, what do I want to figure out? One integral or two integrals? And you look at it and say, well, I don't know how to find the antiderivative of an absolute value function. And I say, well, okay, but your calculator does. And for now, that's all we need. All right. Number 6, a couple of different ways to go about doing it. I like saying that. One thing to keep in mind is symmetry is a thing. You may not know this going in, but the area of the non-shaded region and the area of the shaded region are exactly the same. How do we know that? Well, I know it from experience. You may look at it and say, well, they look like they are, so that's what I'm going with. All right? I don't want to take the chance, so what I'm going to do is find the area of the thing that I don't want. All right, so that's this part. On the interval of 0 to pi, I want the area under 1 plus cosine x dx. So that's that area of the non-shaded region. The area of this rectangle base times height. The base has a length of pi. The height has a length of 2. So 2 pi. So 2 pi minus this, that integral, minus the thing